Welcome to our AP Chemistry Notes over titrations, and this is fit within our acid-base chapter. Titration does not have to be an acid-base thing, and we will come to some examples of that later. But it is super common in acids and bases, so it's a good place to discuss it. Okay, so now I want to talk about the basics of titration, and we will do some labs where you do titration. You'll probably be sick of titration. I know by now you think colorimetry is like the best thing ever in AP chemistry. Well, we're about to do the same sort of thought with titration. You're going to do a whole lot of titrations. Very, very simple setup, very practical purposes. We're going to look at doing titrations, and one of the keys of doing titration is to determine or to use a molarity as you do that. So I just want to remind you some things about molarity. Molarity is, of course, and that's capital M, moles per liter. So formula-wise, molarity equals moles per liter. Okay. But I also want to point out you could write molarity as millimoles per milliliter. And I know that sounds weird because we've never discussed millimoles before, because quite honestly, I don't like them. With the issue of dyslexia I have, converting moles to millimoles by moving the decimal 3 places, I'm certainly going to move it the wrong direction. But it could be done. And especially with the concentrations we really do work with in chemistry, trying to be as green as possible, use as little chemicals as possible, millimoles per milliliter would be fine. And you'll notice that the milli part would cancel in those units, and then you get moles per liter. So a millimoles per milliliter would be exactly the same thing as a molarity. You could do it that way, most definitely. So formula-wise, molarity would be millimoles per milliliter. Okay. And the one that I use all the time, just because I can easily remember 1,000, is I use this format, that molarity is a moles per 1,000 milliliters. Because quite honestly, we tend to have a molarity, but then our volume in milliliters. So to convert from milliliters to liters on paper just does not make sense. Do it in your head, or even better, just start with, instead of writing 1 liter, write 1,000 milliliters, and you're already good to go to multiply by your volume to get your moles or something like that. Now, we're going to use titration with neutralization. That's the point, is to neutralize an acid with a base and calculate some unknown quantity about either the acid or the base, whichever we need to know about. And we do that during neutralization. And neutralization with acids and bases is where we get, and now check this out, stoichiometrically equivalent amounts of acid and base. And we talked in safety long ago, if you spill an acid on the counter, you don't want to just throw paper towel on it to sop it up, because then when you grab the paper towel, you're grabbing still acid. We want to neutralize it. Well, I can pull out some base and start neutralizing it, and most certainly I can go past neutral and make it a basic spill. So it's very important that we understand what it means to be stoichiometrically equivalent. We're going to work on that, but you want to be sure you've got that going on. You don't just want to randomly, oh, I think this is enough. Because it might not be enough, it might be too much. You're just going to rely on luck, and you don't, for your own safety, want to rely on luck. When we neutralize an acid with a base, or a base with an acid, we get this ionic equation. We will form a salt, but the salt will be soluble, and so therefore, as a net ionic equation, just know the net ionic equation of an acid and a base is hydrogen hydroxide yields water. And that's all good there. Okay, so let's do an example. Okay, so this is definitely going to be involving some calculation. So I have 100 milliliters of 0.1 molar hydrochloric acid, and I have 100 milliliters of 0.10 molar sodium hydroxide. I want to know the molarity of the salt produced. Okay, so let's focus. We have hydrochloric acid and sodium hydroxide, and they're going to form, and we'll get back to why that's a one-way arrow later on. They're going to form a salt, which is NaCl, and water. Now notice how this is a double replacement reaction. Most definitely an acid-base neutralization is a double replacement reaction. Okay, so that's helped me focus. Okay, I want to know how much sodium chloride, what that concentration is going to be. Now I'm going to work in moles in my rice table, and whenever you mix an acid and a base together, I strongly recommend making your rice table in moles. And I will prove to you the wisdom in just a moment. When you do initially. Well, initially in molarity, I have 0.100 molarity HCl. And initially in molarity, I have 0.100 molarity sodium hydroxide. Oh, but check this out. Not that. This. Okay. I have 100 milliliters of acid, and I'm mixing it with 100 milliliters of base. What happens all the time when you mix two solutions? If you said dilution, you're correct. We're going to end up diluting the acid and the base. So first off, I want to work in moles. And if molarity is moles divided by liters, then moles is molarity times liters. So there we go. So to find the moles, I need to take the molarity times the, well, let me go this way, the molarity times the liters. Oh, that's not liters, that's milliliters. Okay, so my molarity is 0.100 molarity, which is moles per 1,000 liters. Sorry, milliliters. Do you see how I made that change? Okay, that's why I like doing it that way, because I can quickly take what they've given me and write it as moles per liter. Now I'm going to multiply by the volume in milliliters, and my milliliters cancel. And so it's 0.10 times 100 divided by 1,000. That's actually going to move the decimal. That's 0.0100 moles. Okay. Now here's the interesting thing. We have mixed. So we're expecting to dilute, right? This is the quantity in moles in the mixed solution as well. So there's no reason to account for the dilution here. We will account for it later, most definitely, but not here, because we're out of our molarity. Molarity would be changed by dilution. Moles in total will not. This is a total moles. Now I also point this out. These numbers are the same as those numbers. So I can take that little shortcut and know that I have the same amount of both materials to start with. And if you want zeros in there to hold your place, there you go. Okay, so all I've done so far is taken my initial amounts that was told me in the problem, and I've converted molarity to moles with the molarity and the volume that I'm given. That should not be difficult to do. Practice it if you need to practice it. Okay, I hope you should be able to see that easily. Now let's talk about change. Well, I have lots of reactants, no products. I'm going to lose some. How much do we lose? Now check this out. This is not an equilibrium arrow. This is a one-way arrow. It's a one-way arrow because it's a strong acid and a strong base, and by definition they get one-way arrows. So do I have a limiting reactant situation? Actually, I do not, because it's a 1-to-1 ratio, and I still have a 1-to-1. I'm going to lose it all. For those two reasons, it is not at equilibrium. It's a one-way arrow, so we can assume all reactants that I can get used up to products, and it's a 1-to-1 ratio, and I have equal amounts. So I do not have any sort of a limiting reactant situation. If I lose that much there, I'm going to gain that much here. And now I build my rice table at and I call this, I still call it E. Well, no, I don't do that though. I call it end. No, I don't call it equilibrium because it's not at equilibrium. I just call it at the end. END. So there we go. At the end, here's the amount of salt in moles I have made, and I don't really care about the water because that's not what the question asked me for. All right. If I stop here, I have the wrong answer, because the question is asking me for the molarity of the salt, not just the moles of the salt. So how do I get molarity? Well, that's easily done. moles per liter. Okay, well, I've added 100 milliliters to 100 milliliters. That means I've added 200. I have 200 milliliters together. Are you with me? 100 milliliters of acid and 100 milliliters of base, when mixed, give me 200 milliliters total. Now, there's still in that total that much salt in moles, because the total amount of moles won't change no matter if you add water or anything else. Only adding more sodium chloride would change that. But that's 200 milliliters in 1,000 milliliters. So remember, for molarity, I need moles per liter, so 0.2 liters. So I'm going to take that and divide it by 2. So my final answer is 0.00. I hope I've moved enough decimal places. 0.00 moles. And that's like two additional decimal places there. There we go. So that is the, oh, I got the label wrong. Molarity, moles per liter. Okay, there I've got 0.00500 molarity of the salt produced in this reaction. Okay, so what might have seemed like a difficult question is really not that difficult, and you just work it out in a rice table and let the rice table do the work for you. But here's the catch: whenever you're doing an acid with a base, whenever you're mixing them, and a reaction could occur, do yourself this favor. Work your rice table in moles, so that when you answer your final questions of molarity, you divide by the total volume. That's the key. A lot of students will get it to this point and forget to divide by the total molarity, or they'll just divide by 100 milliliters and not 200 milliliters, and therefore get the wrong answer. So please don't let that happen to you. All right. Now the salt, sodium chloride, and the moles of the salt formed again was 0.0110 moles. The volume was 200, and so we can find the molarity. And I just wanted to show you how this would be calculated either way. I don't think I have enough zeros in my final answer. Oh well. Excuse me a moment. Maybe. Okay, well, here's what we'll do. Don't copy that. Yeah, that's the fun of having a brain that likes to float decimal points without trying. So molarity is moles per liter. There is my moles from my rice table. There's my liters. And I already worked it this way, and that should be 0.00500 moles. Yeah, that should be the right decimal places. Molarity, sorry. But I also wanted to point it out this way. Check out what's going on here. I have millimoles per milliliter. Notice how I don't have to convert from milliliters to liters for this, but what I would have to convert from is from moles to millimoles. So you really are converting one way or the other. I have good friends that teach a really strong AP chemistry course, and they really demand that students work in millimoles most of the time. In my opinion, again, it's converting the top instead of converting the bottom. I'm more familiar with converting the volume, so I'm going to stick with that. Feel free to use millimoles if it works for you. I would hate for you to lose points on the AP exam by using millimoles when that's not what's going to work in your head. So please, please, please figure out if you want to use millimoles, do it, but figure out how to do it right. It does work really handily. You know, you turn your 0.0100 moles into 10 millimoles and you divide by 200, and maybe that's how you see this number even easier. I don't know. Okay, but the millimoles will cancel, the milli part of both labels will cancel, leaving you with the molarity, which is your label. And that's how millimoles works. And that's kind of the point of millimoles, is that it would cancel easily with milliliters. All right. I have 100 milliliters of 1 molar hydrochloric acid and 100 milliliters of 0.800 molarity sodium hydroxide. I want to know the molarity of the solutes. Okay, now remember then, water's the solvent. Okay, so what's that leave? If I'm asking the molarity of the solutes and water's the solvent, what's that leave? Okay, well, it's all right if you don't have an answer to that right now, because let's focus. Let's write our equation. I bet you never expected writing equations to be a focusing help, but it always is. Here's my equation. Strong acid, strong base yield salt and water. Okay. Now let's ask, what are the solutes? Well, here's water's the solvent. So let's hide water. What are the solutes? Everything else there. Check that out. All of the rest of that. That's a solute, that's a solute, that's a solute. So in other words, what they're asking us for is all the rest, except for water. Okay, we can handle it. Let's take care of this. That was my R, so let's do initial. So initially I add 100 milliliters of 0.1 molar HCl. Okay, well, kind of off to the side. I have 0.100 molar, which is moles per 1,000 milliliters. And I'm going to multiply by 100 milliliters. And milliliters cancel, moles is left. So it's 1 times 100. Ooh, that's 100 divided by 1,000. Ooh, that's 0.1. So 0.1 moles. And there's some more significant digits there. But that's not truly necessary until I get to the very end and I looked around. So we'll come back to that thought. I just want to try to keep my rice table not so cluttered. Now what about my sodium hydroxide? Well, I have 100 milliliters of 0.8. So you do the same thing, 0.8 moles per 1,000 milliliters times 100 milliliters. So I have 0.8 times 100, move that decimal 1 2 times, that's 80, divided by 1,000. Now did you catch that? That's 80 divided by 1,000, not 800 divided by 1,000. That's 80 divided by 1,000. So if you wanted to say 0.8, you would be incorrect. And hopefully this is math that you could do in your head. They would expect you to be able to do math like this in your head. That's why I like writing it out this way. So you see, oh, that's actually 80, and then I'm going to divide by 100, so move that decimal. Okay, it's 0.08 moles. How much salt and water to start with? Nada. So I've got C, change. One-way arrow, so I'm going to use up all the reactants I can use up. But how much can I use up? Well, what do you notice? If you said a limiting reactant situation, you're absolutely correct. I'm going to use up all my sodium hydroxide first. And it's a 1-to-1 ratio. Most of the time they are 1-to-1 ratios with acids and bases, which makes it really convenient to do this mentally. Which also means over here I'm going to be adding this much. Okay, so what do I have at the end? Not necessarily equilibrium. Okay, well, 0.1 to 0.02 moles. Do that in your head. If you are grabbing for a calculator to do that, shame on you. You ought to be able to do that in your head. I mean, check it out. You add a 0 there. Well, that's supposed to be 0. And you get 10 minus 8. Okay, that is the kind of math they expect you to be able to do on the multiple choice portion of the test. So practice it till you can do it. 0 sodium hydroxide left because we used it all up. And nice and easy, 1-to-1 ratio we're making. And again, please notice, I checked my ratios. When the biggest danger students get into is in acids and bases, those ratios are like 75% of the time 1s. And then, of course, on the test, they're going to throw in some 2s or 3s, and then you're going to get it all wrong. So always be checking your ratio. Okay, I'm getting off my soapbox now. Let's finish this up. That's the moles I have in total of everything at the end, but what I'm asked for is the molarity. So I need liters. Well, check it out. I'm mixing. What am I mixing? I'm mixing two solutions, and when I mix solutions, I get dilution. I have 100 milliliters, and I'm adding it to another 100 milliliters. Oh, imagine that. That makes 200 milliliters. But I'm going to need liters. Now, again, I could turn these to millimoles. That wouldn't be bad. I'll actually do that down here. 20 millimoles there. Well, maybe I won't do that down there. 80 millimoles there, and 80 millimoles. There's supposed to be two M's there, millimoles there. Okay. Or over here, I have 200 milliliters in over 1,000 milliliters per liter, and so that's 0.2 liters. And there's more sig digs there, okay? So, but I'm just trying to keep my rice table uncluttered at the moment. So what was I asked for my final answer? I was asked to ignore water, so we're going to ignore water. And you don't have to scribble it out. I just want to dramatize my point of we're going to ignore water. Okay. Over here I have 0.08 divided by 0.2. And you're like, what is that? Well, if it's any easier to see as 80 milliliters as 80 divided by 200, then there you go. And you could also do it as 8 divided by 20. Yes, it's going to be a decimal number, but check this out. Divide that by 4 and we get 2. Divide that by 4 and we get 5. We get 2/5. Oh, hey, I know what 2/5 is. It's point, that's a decimal point, 0.4. Well, that's a decimal point. Thank you. Okay, 0.4 molarity. Because the millimoles cancel, or the moles per liter makes molarity, whichever way you want to go to get your molarity. And I had a decimal point there, and I don't know why it wasn't showing up. Okay, let's talk sig digs. I see 3 there, 3 there, 3 there, 3 there. I'm going to say it's probably a safe assumption to go 3, so I'm going to call it that. Okay. Now what do I have over here? Well, check this out. I have 0.02 divided by 2. You should see it already, but you know what? It's okay if you don't see it already. Check out the power of working in millimoles. The milliliters, of course, canceling. 20 divided by 200 is the same as 2 divided by 20. That's the same as 1 divided by 10. I know what 1/10 is. It's a point. Don't know why it doesn't like me drawing decimals. 0.10. I said point. Thank you. 0.10, and I need 3 sig digs because that's what I've determined I started with, and I want to be sure. So I've got that. I've got a 0. And I've got that. And you know what? If you have your rice table lined up nice and neat like that, you probably don't even have to label it that this is 0.100 molarity HCl. They'll read that right off your rice table. Now, if you want to be sure that you're very clear about your answer, that would be a great thing to do as well. So there we go. Again, using a rice table in moles so that at the end we account for the dilution. And that's really what I strongly suggest whenever you add solutions together. Work it in your rice table in moles only, and then put it together at the end with the liters, the total liter amount. Because with adding solutions, you get dilution. And I remind you, just because I'm on the topic, rice tables only ever always work in moles, molarity, or if everything is a gas, you can work in pressure units. ATMs, as long as it's all ATMs, or millimeters of mercury, as long as it's all millimeters of mercury, or torr. But those are the only things a rice table works in. You cannot work in grams. You cannot work a rice table in grams. Okay, so there we go. There's some examples of titration, using some information we know to find things we don't know. Okay, how about this one? Ooh, why did I pick this one? Well, I picked this one because it's going to be different than what you've already seen. So check this out. Let's focus on a reaction. I have HCl, and it's going to react with calcium hydroxide, and it's going to make, in this case, calcium chloride and water. And I don't know why my water didn't stick around. Okay, so there's my reaction. Are you yelling at the screen yet? I hope you are. I hope you're like, Mr. Bellin, it doesn't balance. You're absolutely right, it doesn't balance. Okay, so let's put a 2 there because I need 2 H's. And I'm going to put a 2 there because I need 2 H's. And I needed 2 Cl's, and I need 2 Cl's. Hey, that works. I need 1 calcium, and 2 hydroxides, 2 hydroxides. Now, please, if you can't see an acid-base reaction as water like that, write it out as HOH. No shame in doing that. Everyone does it. Okay. All the cool people do it. There you go. So we're going to write as HOH. So now I can see 2 H's and 2 H's and 2 OH's and 2 OH's. Okay. So that might help you see it better. Okay, initially, what do I have? Well, check out, I have the same amount as I did last time. I have 100 of 1. So that's going to give me, in moles, why won't it let me draw decimals? I don't know. Molarity times liters, not milliliters, or molarity divided by milliliters times liters. Prove it to yourself. Pause the video, work it out on the side, come back. Okay, so I get 0.100 moles there, and I get 0.100 moles there. And I have 0 of that and 0 of that to start with. Okay. And change. Okay, so I have a one-way arrow. I'm going to use up my reactants. With a 2-to-1 ratio, what am I going to use up first? Yeah, I hope you said that I'm going to use up my HCl first. So I'm going to use all of that up. Now I point this out. This would be like subtracting 2x. If I'm subtracting 2x there, I'm going to be subtracting 1x there. I'm going to be adding 1x there, and I'm going to be adding 2x there. I mean, that much that you should follow from our previous work with rice tables. Okay, so with that said, I have, if I'm subtracting 2x there and 2x equals 0.100 molarity, I mean, write this out on the margin if you need to. Negative 2x equals negative 0.100 moles, therefore x equals, and solve for x. But hopefully you can see in your head, I'm going to be subtracting 0.0500 moles for a single x, and I'm going to be adding a 0.0500 moles for a single x, and I'm going to be adding a 0.100 moles for a 2x. Okay, and then at the end. Doesn't seeing the x's help that? I really strongly feel it does. So don't be afraid to do that. Even if you know you're going to know what your x is, feel free to write it. So again, you check your ratios. It forces you to check your ratios, and that's always a good thing. Always, 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 always check your ratios. Okay, now I'm going to totally ignore this line as I make my my end line. So I have 0 there. I have 0.0500 moles left over there. That's a 5, sorry. I have 0.0500 moles there, and I'm asked for solutes and not solvent, so I'm not going to really care about my water. Okay, now I'm ready to answer my question, but I have moles, and I need to make that molarity to answer my question. So 100 and 100 is 200. So I'm going to have 0.200 liters as the volume. Okay, so how do you want to view this? Hey, would it help? Let's view it in millimoles and milliliters. We can do that. It's just moving the decimal 3 times. That's going to be 50 millimoles divided by 200 milliliters. Hey, I've got 5 divided by 20. Divide each of that by 5, I have 1/4. Ooh, I know what 1/4 is. 1/4 is a 0.25. And to have 3 sig digs, I'm going to add the 0. And since those are identical, I know the answer here as well. So there's my answer for the molarity of my solutes. So being able to work in millimoles really can help the mental math. Now, if you're given a calculator, if you're allowed a calculator, yeah, it doesn't really matter. And with practice, you could even, 0.05 divided by, I crossed out too many zeros, my bad. It's those zeros that cancel out. Be sure you watch your places. Okay, so 0.05 divided by 0.20, hopefully you saw, oh yeah, that's 5/20ths. Okay, so maybe it's better exemplified here, where it's lined up better. There you go. So, one way or the other, either get comfortable with millimoles to do the mental math, or be able to do it in decimal form like that, or go, hey, I at least have it lined up. Let me move both 2 places and, 5 divided by 20. I can handle that. They could expect you and would expect you to be able to handle this kind of math on the free response, the multiple choice portion. On the free response, you'd have a calculator and you could still be asked to do this math. But these numbers would be good numbers for mental math on the multiple choice. All right, so we're going to leave off with this because we're running out of time, and we have a lot more to say about titration, so that'll be coming up in the next video. So I want you to pause and give it a try, and then see what you get at the end. I do point this out. It's asking for what is the salt, so you need an answer. Well, you can't really see black at all, can you? So you're going to need an answer of what the salt is, and then I want the concentration. Remember, concentration better be in molarity. Moles is not a concentration. Moles per liter is. So pause the video here. Yeah, seriously, pause the video. Turn it off. Pause it. You know you want to. Okay, you know you have to. Yes, you with the glasses, or not the glasses. Have you paused it yet? Okay, so you should have paused it and come back, and we're going to run through this super fast because it's nothing new. It is just a reworking of what you've already done. Double replacement and reaction. I'm going to write water as HOH just because I'm cool that way. I'm going to balance everything. Oh, hey, look, that works. Okay. So what is the salt? Well, the salt's obviously potassium sulfate. So there's my first answer. Now, I want to know how much molarity of potassium sulfate I'm going to get. So I have a, interesting numbers. I have a 0.1 of that moles. And again, I'm working in moles. So I'm taking my molarity times my volume per 1,000 milliliters. Okay. So I have 0.1 moles there. Now check this out. I have 1 mole. I should be writing this way out to the side. Sorry, I'm not. Per 1,000 milliliters. And I'm multiplying that by 200 milliliters. So it's not just a 1 times 100 to make 100 divided by, this is 200 divided by 1,000. So I have 0.2 moles of that. So I hope you caught that. Okay, so over here, I started with, I didn't need an arrow there. Oh well. 0 of each of those. Okay, change. Well, I have a one-way arrow, so we're going to use up acid and base. Which one are we going to use up first? Which one's our limiting reactant? Ah, did you see it? I have a 1:2 ratio there, and I have a 1:2 ratio there, meaning I'm going to use up everything. What if you don't see that? That's fine. Start this way. I'm going to subtract 1x there. I'm going to subtract 2x there. I'm going to gain 1x there. And if I cared about water, I don't really care about water, but I would have gained 2x there. Okay. Why don't I care about water? It wasn't asked in the question. What's that work out to? Well, if 0.1 is 1x, then I'm going to lose 0.1 moles. And if 0.1 is 1x, then 0.2 is going to be 2x, so I'm going to lose 0.2 moles. Already see what happened there? I get 0 leftovers. For some reason, we mix them in exactly the right ratios that we should have 0 leftovers. Okay, so is it really a limiting reactants question? No, we just are using up all of our reactants. All right, then over here, as I said, if 1x is 0.1, then I'm going to gain 0.1 moles. So I have 0.1 moles of potassium sulfate, my salt, in, I need moles per liter. Well, I've added 100 plus 200, that's 300 milliliters I've added in 1,000 milliliters. So that's a 0.3 liters. I don't know why I'm trying to add to that label, sorry. 0.1 moles in 0.3 liters. Oh, well, we can do that. That simplifies to 1/3, 1/3. 1 divided by 3. You with me? Move that decimal 1 if you need to. Okay, whatever you do to the top, you do to the bottom, and you're still safe. So my molarity is 1/3, or 0.3333. And since I have 3 sig digs going on, I'm going to just call that 0.333 molarity. That is the molarity of my salt that I have going on. Okay. So there's another great example. I hope you got that answer. I hope you paused it and actually worked it out. You're only cheating yourself. The entire goal of this year is to prepare you for the AP exam in May. And your grades along the way, in my opinion, do nothing but tell you how close you're getting to being ready. So to be like, oh, well, I don't need to, I'll just see it when he shows it. Okay, you're really just fooling and hurting yourself. Don't lie to yourself. Pause it, work it, see how you did. Besides, we have lots of these to do in class, so if you don't see it now, you're going to be hurting when we do our in-class work anyway. And again, your grades are simply an indication of how well you're mastering the material. It all matters come May. So be sure you're putting in that effort. All right, that's all we have time for today. There is still lots more to discuss with titration, so I will see you next time.